All right, so I've gotten a few questions on how to connect a physical situation, throwing a ball in the air or a car accelerating away from its stop sign, et cetera, et cetera. Those situations to position, velocity, and acceleration, and what the graphs of those things would look like for these various objects. And we talked a little bit about that in other contexts, and you've got some of that in your textbook reading. But I do think it's important in building a conceptual set of knowledge about these fundamental quantities describing the motion of objects. So let's take a look at a situation where we have a ball that we're going to throw up into the air with some initial velocity. And it'll go da, 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 and say we're very good and we managed to get it to go basically straight up and straight down. And then we're going to catch it again at the same point. So it'll stop right there in our hand. All right. So let's start with that situation and see where that takes us. So first, let's look at acceleration. All right. So if we just look at the portion of the movement of this object where it is in free fall, in other words, it's left our hand here, and it is coming back to our hand, but we're looking at the snippet of time just prior to it hitting our hand and stopping. Then if we graph our acceleration versus time, so if we get our acceleration here, there we are. Well, we know, or should know, that an object in free fall, that means it's only under the influence of gravity, and the acceleration due to gravity near the Earth's surface is, near as makes no difference, 9.8 meters per second squared. Now, as to whether that is a positive 9.8 or a negative 9.8, that all depends on our coordinate system, right? So why don't I grab a different color here, and we'll make ourselves a little coordinate system, easy to do for this kind of thing where everything's moving in one dimension. And so upwards is positive, downwards is negative, and so our acceleration, because gravity tends to accelerate things back down towards the ground, towards the center of the Earth, then our acceleration here is going to be negative downward and 9.8 meters per second squared. I won't bother putting in the number here, but it's constant and it's negative during this whole time when the ball is not in contact with our hand. It's just flying through the air. Okay. And that, by the way, is for the entire trip. It's all the way up and all the way down, okay? That's the acceleration, because the reason, well, one, occasionally people get bound up in thinking, oh, well, somehow it changes direction when the ball's motion changes direction, right? Where it gets to the top and it was going upwards and now it's moving downwards, and somehow the acceleration has to have changed for that to be the case. No, acceleration is always pulling downwards. On the way up, it's taking a positive velocity and making that velocity smaller and smaller and smaller and smaller until briefly velocity is 0 up here. And then on the way down, it's taking a 0 velocity that it has right up here at the top and making that negative velocity as it goes downward bigger and bigger and bigger and bigger, all right? Because the acceleration is then in the same direction as the velocity of the object. Right? So this is all consistent with what we've been saying thus far. Now, if we want to put velocity on this graph, and maybe since I made the trace for acceleration, I should make that black, and I should go over here, and maybe I'll get blue for velocity. We'll put them on the same axis. Now, if we have velocity, well, it starts out with an initial velocity that is upward, right? So positive. And that means that we're going to start our velocity at some arbitrary point. Let's say it's right there at time 0. That's going to be our v0. Now, acceleration is constant, so we know that our velocity graph needs to have a constant slope, because the slope of the velocity versus time graph is equal to the acceleration at any point, all right? And because the acceleration is always this negative 9.8 meters per second squared for an object in free fall, then we have a constant negative slope. Let's see how well I can draw that. Like this, okay? Now, I've gone on a bit too long there, probably. We'll talk about why, and we should probably have equal bits above and below the axis, but we'll come back to that. Okay, but constant negative, and starting at a positive v0, our initial velocity. Okay, now, lastly, let's look at position, and we'll go green for that one. Now, position, if we call the origin where the ball leaves, so we'll say this is x equals 0, that position, and we're saying it comes back to that same position at the end, and we need to remember a couple of things. One, that this is not going to be a straight line, right? Because the slope of an x versus t graph is equal to the velocity. And the velocity is continually changing for this ball, right? That's the blue curve. So we want to start at 0, and we want to end at 0. Let me pick out a good spot here, okay? And the question is, okay, well, what does it do after that? Well, it's going to go up to some maximum height. And in between, we know that it's going to have this t squared dependence. It's going to be a parabola. And because we have a negative acceleration, we're going to expect a sort of concave down parabola here. Okay, something like that. Okay. Let's talk a little bit about why that is. Okay. We've looked at these situations before, but to reiterate, right, the velocity is large here at the beginning, and so the slope of our x versus t line here is quite steep. And then the velocity gets smaller as we move down the curve, and so the slope of our x versus t graph as we go along gets flatter and flatter and flatter until here, right at the very top, right at the very top, when the velocity is briefly 0 here, then we're at our maximum height there. And then it starts going back down towards our hand at that point, hand here at that point, or just after leaving the hand and just prior to returning to the hand, okay? And this would be the max height. All right, and that corresponds, if I go back to blue, that corresponds to v equals 0 for an instant as it's sort of turning around and coming back down towards the ground. And during that whole time, acceleration is still downward due to gravity. Now, the reason I said earlier that I drew a little bit too much here, and let me break out orange just to make the correction, is that I want to cut it off right about there. Okay, all this over here shouldn't be here. Now, why? Well, if acceleration is constant, and if you're leaving from and coming back to the same position, well, then the initial velocity upwards, so this right here, that you leave the hand with, should be exactly the same magnitude of velocity that you return to the hand with, albeit going in the opposite direction, so at sort of the final state. And we know that because the amount of time it takes a acceleration like this to take an initial velocity that's upward and turn it to 0 up here at the top again, and then take that 0 velocity and turn it back into a negative velocity that gets back to the same position, those two periods of time are the same. So it's accelerating for the same period of time, so its velocity is going to change the same amount, and its position is going to change the same amount. And so we should see roughly equal bits of this blue curve above and below the axis, this axis here, okay? So, went into a lot of detail there. I hope that's helpful for an object in free fall, and we'll be talking about other situations as time goes by, but I think we've probably gone on long enough about this particular example for now. Thanks for listening and viewing, and I'll see you later.